Okay, my name is Yulia Petrova. I am from Kiev, from National Aviation University, and I would like to represent our report, Mathematical Model of Test Fire during Certification of Smoke Detectors. Next, please. My co-authors are Alexander Solomentsev, Maxim Zalysky, Olga Sherbina, Anatoly Taranenko, and Yevgen Gabrusenko. Paper outline. Introduction, state of the art, proposed methodology, and conclusions. Fires are a significant challenge in modern times. The development of organizational and technical management to detect and prevent fires is one of the key aspects of ensuring human life and preserving material values. Detection of fires in the initial stages is carried out with the help of different types of detectors, such as thermal detectors, smoke detectors, flame detectors, and others. The specified features imposes the requirements of fire detectors in terms of reliability of operation, accuracy, and efficiency of fire detections. Verification of established requirements is carried out during the certification tests. In Ukraine, there are new standards that regulate the method of conducting certification tests for fire detectors. The process of certification of fire detectors includes different types of tests, such as repetition test, a test for analyzing detection direction, impulse test, and others. The main type of certification testing for smoke detectors is testing them in special test fire rooms. The process of improving existing and creating new detectors has a certain sequence. From the development of the technical task to certification tests. For this, relevant regulatory documents, of course, can be used, as well as specialists, special equipment, consumables, and other can be involved in this process. At the current stage of development of scientific and technical thought and information technologies, it's appropriate to conduct mathematical modeling of the entire process of development and improvement of fire detectors, in particular the process of certification tests. The following consideration can be made regarding the attractiveness of using modern tools and computer technologies, such as saving consumables materials, the possibility of timely regulation and adjustment of the design of the products under development, shorter testing time, safety of the testing process, and others. To implement the certification process, it's necessary to perform several works, such as create a mathematical model of the actual fire detector, develop a mathematical model of the process of burning consumables, develop a simulation program, and plan a virtual experiment. Perform a synthesis of the data processing procedure regarding the simulation result, and the last perform verification and validation procedures. As an object of research, we will consider the main types of fire according to the classification in the standard. First, the wood pyrolysis smoldering. It's TF2 type. Cotton burning. It's TF3 type. open burning of synthetic materials such as polyurethane. It's TF4 type, and the last TF5 type is open burning of liquid such as an heptane. For the mathematical modeling of the certification process of smoke detectors, it's necessary to take into account the mathematical models of all the physical and chemical processes that accompany them. These models can be used to check the main parameters of smoke detectors. The purpose of our research is analysis of combustion process, the mathematical models building for the combustion for various types of fires, as well as the identification of method for testing fire detectors in the special fire test room. The mathematical model building aims to establish the functional dependence between several parameters or several variables. Mathematical model building includes several stages. So, as the first stage of modeling, it's appropriate to conduct an analysis of the vector of input variables common such as amount, distribution, the physical and chemical properties and condition of the surrounding materials such as humidity and so on. The output values are considered to be dimensionless, loss of the fuel mass, combustion coefficient, fire alarm system activation time, and others. At the next stage of modeling, analytical dependencies between vectors of input and output variables for all types of fires are established. Thus, for a TF2 type of fire, it's appropriate to find the dependence of the relative weight loss on time, uh, presented in the form of partially continuous function at each of the flame propagation intervals. For the TF3, it's necessary to solve the Cauchy problem of the mass balance differential equation and therefore to determine the activation time of the fire alarm system under the specified test condition. And for fire types TF4 and TF5, we can perform calculation of the optical smoke of the environment and combustion coefficient. At the last stage, it's appropriate to construct graphical dependencies of the optical smoke of the environment and the relative weight lost of the combustible material over time, which would be used to compare the result obtained during the test with the requirements of existing standard. So, in the case of TF2 fire, the dimensionless mass loss is a function of various, following various, and it's presented by the formula 1. Such variables may be working weight of wood, release of volatile substance or mass loss, the moisture content of the working mass, and other parameters. In general case, the equation of the kinetic curve will be take the form of a piecewise continuous function as it presented in the formula number 2. On the basis of the previous equation, equation number 2, when using experimental data, it's possible to construct a kinetic characteristic, as it presented here in the figure 2. And using the same experimental data, the flame propagation process we describe by the graphic in the figure number 3. The dynamics of smoke in the area in the initial stages of the fire, its first 10 or 20 minutes, for fires of type 2, 3, and 4, is determined by mass balance equation by the equation number 3. And in the case of TF3 fire, the burning area is defined by the equation number 4. Then substituting this equation in the formula number 3, we obtain the following dependence, our equation number 5, and as you can see, it's a differential equation with separable variables. And then we solve the Cauchy problem for equation number 5, and using equation number 5 and next integral, we can get the time since the fire started. It's our formula number 6. And solving equation number 5 for real conditions of the TF3 fire in the test fire room, we can build the next dependence that you can see in the next slide. Is dependence of the attenuation index in the smoke zone on time. In the case of the TF4 fire, it's sufficient to solve the consumption equation of Pauli fraction direct flow layer, described by the formula number 7. And the solution of equation 9 we can represent graphically such as dependence of the full dense height of the direct flow layer on the degree of burnout at the largest particle. And in the case of TF5 fire, according to the diffusion theorem, in the event of the absence of appreciable heat transfer by radiation of the combustion zone, we can determine the combustion coefficient, which represented by the formula 8. And then, as a final step, and using equation of thermal conductivity and diffusion, we express the such ratio of temperature of smoldering and temperature of burning by the formula number 9. So the obtained equation can be used to improve the methodology of conducting certification tests for smoke fire detectors. And for example, for the TF5 fire, it's a significant increase in the temperature near the ceiling. But for the other types of fire, it remains relatively constant value. So we conclude that it's advisable to test the detectors for the impact of the TF5 fire. The last. The obtained analytical equation allowed to form the conclusion regarding to the creation of whole system of computer analytical support for the design and certification process of various fire detectors. The main advantages of the system of computer analytical support for the design and certification process of fire detectors are the ability to continue testing for the considerable time, the opportunity to research on various construction of fire equipment, to the availability to work out various optional for the principle of operation of the equipment. There are no restrictions for limited number of samples for research. The veracity of research result will be at high level, the number of personnel decreases, and the probability of dangerous situation also decreases. The environment of artificial intelligence technologies for processing data from test results and the possibility of creating and attracting data hubs. And conclusions. Our paper considered the mathematical model of test fires, which can become the basis for carrying out the following improvements during certification test of small detectors in the test fire room, such as improvement of control and measurement equipment, modernization of and creation of new equipment for the test fire room, improvement and implementation of new, more advanced automated control system, optimization of test fire conditions, and evaluation of the certification test results according to the given mathematical model. And should be noted that the given mathematical models can be used to qualitatively assess the feasibility of using one or another smoke fire detector in specific environment conditions, as well as the conformity of the parameters declared by the manufacturers with their real values. Our future research direction will be associated with developing a mathematical model of the smoke detectors and its verification during the test fire in the certification laboratory. Thank you for your attention.
Thank you very much. Thank you very much. Dear colleagues, do we have a questions? There are any questions?
Okay, I can ask some questions. Very interesting topic. It connected to so dangerous experiments with fire, and I understand that it's very difficult to organize these experiments, especially when you told us about. Oh, this slide, please. You told that the pressure in sail it increases and so on. So a lot of things. As for me, it's interesting. You proposed mathematical models and theoretical description of different types of fires. But did you match the result of your mathematical model calculations and the real experiment?
Is our next step for the research.
Okay.
We plan in the future to do this.
So we should expect a new article around this topic, correct?
Thank you.
So do we expect new article, right? It would be new article around this topic.
Can I add some information?
Yes, sure. Please go ahead.
Let's go. So we have the test fire room in one of our enterprise where our students passes the practice lessons. So this is certification lab of fire detectors, and our students burn these fires. So this is 4 fires that we need to conduct, where we test the fire smoke detectors. And we have some data from these tests, and this data coincides with obtained mathematical models. But we need the next step. We want to do not burn the fires and to develop the virtual lab where we have some model of our smoke detector, so we can measure some parameters before burning fires, and we can make some prior decision about detection of different types of fires. So this work is done approximately by 50%. So we develop the mathematical model of fires. It coincides the real data, but we don't have the model of fire detector. So the next step will be the development of model of fire detector.
Thank you very much for additional clarification.
May I ask another one question? Irina, may I ask another one?
Yes, please go ahead.
Thank you very much. And I'm interested in standards. Do we have any standards of testing fire detectors?
Yeah, we have standard according to European norms. This is standard EN 54. The new version of this standard is according to 2022 year. So, and according to this standard, we have the standardized procedure for testing fire. So we analyze the vibration, test for vibration, test in fire room, test to heat, and so on. So there are approximately 20 different tests that we need to implement to fire detector and whole fire alarm system.
Thank you very much.